Okay, so today we will be discussing Gaussian density, but not just for one variable, for many real continuous random variables together. So that will be called the jointly Gaussian. Gaussian is sometimes also called normal. Jointly Gaussian random variables. This jointly is sometimes also called multivariate. There are different names. So here we are given capital N real continuous random variables, say x1 dot xn. They are jointly Gaussian. So every experiment I will observe them together. They may have a relation between them. One can be temperature, another can be humidity, another can be anything. They will be called jointly Gaussian if they are joint probability density. We have discussed what is joint probability density for two variables x, y, then for three variables. So in general, the joint probability density, if it takes a particular form, then it will be called, they will be called jointly Gaussian. Before that, let us see that suppose x is the vector, there is all the random variables in stack, they are put in a stack in a vector. We have already discussed it yesterday towards the end, same thing I am saying. And a mean vector, it is a vector of mu1 is the mean of expected value of x1, mu2 expected value of x2, mu n. Then we know we can take the deviation, the increment vector x minus mu. There is every random variable, the incremental value it takes around its mean, x1 minus mu1. So sometimes can be positive, sometimes can be negative. And for all other variables. So they are in a stack, x1 minus mu1, x2 minus mu2, xn minus mu n, that is what this is. Okay? We have seen that this vector, if I take expected value of this is a column vector and its transpose, we have seen in the last class, that is the covariance matrix. See, maybe you can say xx, because one x minus mu comes here, another x minus mu row vector comes here. You multiply one element here, one element here. So this has x, this has x. So two elements of x get multiplied. Maybe x1 minus mu1, x3 minus mu2. So x1, x3 terms come. That is why we indicate it by 2x. It's a second order thing. Two random variables are multiplied. It's called the covariance matrix. Okay, for this random vector. It's a random vector, everybody is a random variable and they are jointly random. So this we discussed last time. Mu is the mean. All right. Then these random variables x1 dot xn jointly Gaussian if they are joint probability density, that is p capital X1, capital X2 dot capital Xn and the values x1, x2 dot xn, that takes this form. First 1 by 2 pi n by 2. Okay. And then determinant of this matrix Cxx, its square root, positive square root into e to the power into, I don't have space here, so I am writing here, e to the power minus half this vector, this difference vector x minus mu So you are choosing x1, x2, xn. So you are putting them in a vector, subtracting the mean vector from them, that is x minus. So you are putting those values. So for those x1, x2, xn, so those values of x1, x2, xn you have to put here in the x vector, corresponding mu values, mu1, mu2, mu n in this vector. The column vector, so in the formula they come as row, column transpose is row, then Cxx, and I am assuming Cxx matrix is invertible. That is, the inverse exists. Not all matrices are invertible, but we are assuming when we can assume that we will discuss later, assumed to be invertible. That is, Cxx inverse exists. So again, Cxx was a matrix, its inverse is a matrix. Matrix, then again the same vector, x minus mu. Now this is a column vector, this is a matrix times a column vector is a column vector. So this is a column vector, this is a row vector. So row into column is a scalar. So e to the power minus half into some scalar. So it is a scalar, 2 pi to the power n by 2 scalar, determinant is a scalar, because probability cannot be a vector, probability is a scalar. So whole thing is a scalar. So in the case of jointly Gaussian random variables, this should be the joint probability density. If capital N is 1, there is only one random variable, then you will see this boils down to our well-known Gaussian density function for one variable. That is, if you take n to be 1 only, then obviously 2 pi to the power n by 2, n is 1. Okay, so you have got I am writing here n equal to 1. You see 1 by 2 pi to the power 1 by 2. So 1 by root 2 pi. Then Cxx. Cxx, x has only one element, x1, and mean is mu1, whole vector. So Cxx means what? It was a column vector earlier into row vector, but now column has only one element, x1 minus mu1, corresponding row also has only one element, x1 minus mu1. So it is nothing but x1 minus mu1 whole square, expected value of that, and that is called the variance, sigma x square, sigma x1 square. Okay, and now square root, so it will be just sigma x1. Okay, x1 is a variable, sigma x1. Then e to the power minus half, again x minus mu transpose has only one value, x1 minus mu1. Matrix is a scalar now. That was, as we told, the variance. Cxx is the variance, sigma x square. So inverse of that is 1 by sigma x square. So you have got minus half. So how 2 I bring here, sigma x square I bring here, the scalar, and x1 minus mu1, again x1 minus mu1. Only one element, one element. So this is what you have for the normal ordinary Gaussian density. We all know general form of the Gaussian density function for one variable, but this is more general. Okay, if this happens, then they are, of course, they are real and continuous. If they are complex, then the formula will be more general, more modified. That we will not consider in this course. If you are interested, you can consult books. Now we will see a very interesting thing. Earlier I had said that if a set of random variables, they are statistically independent. That is, if the joint density is product of individual marginal densities, then they are also uncorrelated. Okay, their covariance is, between any two element, covariance is 0. Okay, between any two element. Covariance between any two element 0 means What will be this matrix? It will be a diagonal matrix. Because if you take ith element, in the previous class we have said, if you take ith element and jth element, ith comma jth element, that will be xi minus mu y times xj minus mu j product and their expectation, which is a correlation, covariance between xi and xj. If I and j are not same, then if they are uncorrelated, this correlation is 0, which means if I and j are not same, that is, I am not considering diagonal entries, because for diagonal entries, same I, same j, 1, 1, 2, 2, 3, 3, 4, 4. But if that doesn't happen, then other elements are 0. So, for if the variables are uncorrelated, then the covariance matrix is a diagonal matrix. Okay, that we have seen. Let me again elaborate this. We have seen this I did in the last class though. Cxx was all right. So, this is a vector, the column vector, this is a row vector. So, multiply, you get a matrix. I comma jth element of this matrix Cxx I comma j, this is a symmetric matrix that you have seen. At that time only I showed I comma jth element will be what? ith guy, ith element of this vector and jth element of this row vector, they are product and expectation. So, E with respect to xi, xj, only they matter here in that product. So, xi minus mu y and xj minus mu j. And I and j, if they are not same, they are two different random variables. So, you are taking increment of this around the mean, increment of this around its mean and multiplying and expecting. So, that is correlation or xi, xj. So, if xi, xj are uncorrelated, this will be 0. That means, as long as then I and j, I comma jth element and I and j are not same because they are different random variables, then only I can talk of their correlation. If I and j are not same and they are uncorrelated, then that element is 0. That is, I comma jth element is 0 if I and j are not same. If I and j are same, it will be xi minus mu y, again xi minus mu y, because I and j are same. So, xi minus mu y whole square expected value, which is variance. So, I comma ith element, which is ith diagonal element, will be sigma xi square, variance of the ith element xi. So, diagonal element will be the variances, but on off diagonal elements will be 0. When the elements are uncorrelated. Now, I had told earlier that if a set of elements are statistically independent, we can show they are uncorrelated. That is, a correlation between every two elements there, covariance between every two elements there will be 0. But the converse is not in general true. That is, if a number of variables they are given to be uncorrelated, that is, covariance between any two is 0, it does not mean in general that they are statistically independent. That is, overall joint density will be a product of individual marginal densities, except in the case of jointly Gaussian random variables. Then one means the other and vice versa, both are equivalent. That is what we will see here. Now, suppose we are given the fact that x1 to xn are uncorrelated, meaning Cxx I comma j 0 if, as I told here, if I not equal to j, and Cxx ith diagonal entry, so I comma I, what will be the variance sigma xi square, okay, variance of xi. Fine. So, suppose this is given and of course, they are jointly Gaussian. Then what happens? Determinant number 1, determinant of Cxx. Now, Cxx is a diagonal matrix. All other elements are 0, only diagonal elements are sigma x1 square, sigma x2 square, sigma x3 square, dot dot dot, their product. So determinant is sigma x1 square, sigma x2 square, all right. So in that Gaussian formula, p x1 x2 dot 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 xn, we remember x1 x2 dot 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 xn, we had 1 by root 1 by 2 pi whole to the power n by 2. Okay. And then in the denominator had positive square root of the determinant. So if you take positive square root, it will become sigma x1, sigma x2, sigma xn, like that. So what I do, the whole probability density function I write as a product of some terms, one term, similar terms. One is just root 2 pi, but I had 2 pi to the power n by 2. So I should have 1 by root 2 pi, again 1 by root 2 pi, again 1 by root 2 pi, dot dot dot, capital N times. So I will have maybe 1 by root 2 pi here, dot dot dot, lastly again another 1 by root 2 pi. Capital N number. Okay. Then sigma x1, sigma x2, sigma xn, that is I am taking positive square root, this product. So I take sigma x1 here, I take sigma x2 here, I take sigma xn here. So if you multiply the denominators, you get back what we had earlier. Then e to the power is something that we have to see. What we had, e to the power, this is where I do the calculation, we had e to the power minus half cxx inverse x minus mu. Okay. Now cxx inverse means what? Cxx is a diagonal matrix. All diagonal entries are positive because they are variances. So inverse means it will be again diagonal matrix, but it will be like sigma 1 by sigma x1 square, dot dot dot, 1 by sigma xn square, and 0 on this side, 0 on this side. This is cxx inverse, this matrix. And then you have x1 minus mu1 top guy, then next is x2 minus mu2 dot dot xn minus mu n, and of course this term. So when you multiply this with this, the diagonal matrix, so you have just this multiplied by this multiplied by the next one, this multiplied by this. So you get a row vector, same but their scale. This is multiplied by this is multiplied by, like that. With that, if I multiply x1 minus mu1 dot 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 xn minus mu n. So this, after this product, if I do the multiplication, you will have x1 minus mu1 here and here whole square divided by this plus, really plus because a row vector and this matrix times this is a column vector. So row into column means term by term multiply and add plus. So x1 minus mu1 into x1 minus mu1 by sigma x square, x1 square, plus x2 minus mu2 here also. So x2 minus mu2 whole square by sigma x2 square, plus dot 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 dot. So e to the power some terms which are summed. That means I can separate them out. While e to the power minus half is common, one term will be just x1 minus mu1 whole square by this, another will be dot dot dot, another will be you can just multiply this exponentials you see, so they will add up. The exponents powers will get added up and you will get that. But this is what? This is the Gaussian density of the single random variable x1. This is the Gaussian probability density of a single random variable x2. When they are jointly Gaussian, they are individually Gaussian also. Okay. That is the meaning. I forgot to tell. If they are jointly Gaussian, they are individually Gaussian also. So that means this is nothing but the probability density of this guy, capital X1. This is nothing but probability density of this guy, dot dot dot. This is nothing but probability density of Xn. So you see now in this case, overall joint density is a product of the individual marginal densities. So they are statistically independent. So in the Gaussian case, if you are giving the variables to be uncorrelated, then they are statistically independent also. Converse is always true, but this is not always true. This is happening in the case of Gaussian. I mean, it does not happen in the case of other well-known probability densities, but here. All right. This is one important thing. Another thing is complex random variables. All right, complex random variables. Here, I will say Z is a complex random variable if there are two real variables, two real continuous random variables, capital X and Y. So, I conducted experiment. I observed two real valued, continuous valued random variables, say capital X and Y, and I take their values and write in this form. A resulting variable I call a complex variable Z. Then obviously Z is also random, but it is complex. Then Z will be called a complex random variable. It has got two real random variables. So therefore, even though Z is a single random variable, it has actually two. So I should have one X is capital X, capital Y. So Z will be, maybe if you take this to be small x and this to be small y, so this point is Z, small z as small x plus small jy, this point. And then if I go by dx, and this is by dy, then this is, you understand one thing, dz will be dx plus z dy, right? So dx plus z dy. So this point is nothing but small z plus dz, because x and dz means dx, so x plus dx, and take j common, okay, j here, and in dz and j here, so j into y plus dy here. Y plus dy is this much and x plus dx is this much. So x plus dx plus j times y plus dy. Okay, this is dz. So dz is dx plus j dy, dx plus j dy. Okay, and originally z. Add the two phasors. So j basically x plus jy, and it is dx plus j dz. So x plus dx in z plus dz, and j common y plus dy. So this point. So that means probability of capital Z lying between small z and z plus dz is equivalent to, what will happen? That is, capital Z will lie between these two. This means it will lie within this box. It will fall anywhere in this box. That is the meaning of this. That means it's same as probability of capital X lying between here to here simultaneously with capital Y lying between these, which we know is nothing but Pxy joint density small x small y dx dy. Okay, so when expressed in terms of xy, the real and individual component, real and imaginary components, then their joint density. That will be same as the probability of capital Z falling here. Well, if it is same, capital Z lying here means capital X lying between here to here, capital Y lying between here to here. So the two things are two events, okay, are same. Capital Z falling in the box is same as capital X lying from here to here and capital Y lying from here to here. So this probability and this probability are same. All right. Now, given a function which could be complex or real, f of z, then it takes z, it can give you a real number or it can give you a complex number, doesn't matter, fz. Every time you find a z, there is some x and y, you put that value x plus jy here and get a value. Since that is random, this function also takes value randomly. So what is the expectation? Ez fz. It is same as if you write working in terms of z, if you write it as x plus jy, then what is the meaning of this? This Ez, there is fz taking a value from within, I mean, when capital Z falls anywhere within the box, since the widths are infinitely small, we assume the value of fz doesn't change. It will have the same value as here, at this small z or at this value, at this pair, okay. But chance of that, I mean, it will not always happen, so I have to multiply it by the chance. Chance means you have to multiply this f of z value, that is f of this value, by the probability of capital Z occurring here or equivalently this capital X occurring, capital X Y occurring in this box. So that is, I have to, when I express Z in terms of x y, I have to multiply this by the joint density. And then average, okay, multiply everywhere and take average. Then, as we have done many times in the past, weighted average. So this to be divided by summation of the weights. Weights are this part, but their average, their integral is 1, certainty, probability of certainty is 1. So we get this, which is nothing but E x y of this function. F, now you write in terms of x y, x plus jy. All right. Then one thing, Ez, suppose this is given, and I suddenly, and f of z is a complex function. So it takes z as argument and gives you a complex number, f of z. Now, instead of f of z, I take the conjugate. That is, whatever value f of z takes, I take a complex conjugate of that. So then it becomes a function f star z. F star z. What will happen to that? So again, just same thing I have to do, but instead of f, it will be f star small x plus, these are small. Within the integral, there are the variables of integral. So now you see, probability density is real, it is never complex. Dx dy real, and this is star. So I can as well take the star out. I mean, this product, I can put the star outside, because star of a product means star will be put on everybody, but they are real. So no change. So this product and star and then integral. Integral is a summation. So summation of complex quantities with a conjugate, you will get the same thing if you first sum and then conjugate. That is Z1 star plus Z2 star. That is first conjugate Z1 star, Z2 star, then add. That is integral. You will have the same thing if you do first addition Z1 plus Z2, then star. That is Z1 star plus Z2 star, we all know is Z1 plus Z2 star. First add. So first you integrate and then star. That is first you integrate and this product but this is what I have here. So that means this will be nothing but Ez of the original function f z and then star. So if you are taking f star z and then expectation value with respect to z, what you have to do, you have to first take the expectation value of the original fz, no star, and then put star on that. And implication of that is, suppose fz is z. So that means Ez fz star is z star, and z is suppose mu plus, sorry, 1 minute, z is suppose x plus jy. Okay, Ez z star will be what? First you have to take Ez of z and then star. Ez of z means expected value of this plus j times expected value of this. So that was mu x, this was mu y, expected value. So mu x plus, this is mu x plus j mu y star, which is same as mu x minus j mu y. So this is very important. If you have z and you are taking expectation of z star with respect to z, it will be original expected value and then conjugate, so mu x minus j mu y. So I stop here, and we will build upon these complex random variables, and in particular we will consider complex covariants and complex covariance matrices in the next class. Thank you very much.